let me start this with that. All of the catalysis that we have, all of the catalytic mechanisms that we have talked about from the beginning up to this point now, they are carried out without changing the whole mechanism of the reaction, or let me say without changing the pathway for a particular reaction altogether. Because in a way, even though we are saying that this one is probably this one is trying to stabilize this, it's not probably as though this proton will do what will leave here, but in a way this proton will be much more closer to this oxygen to probably balance the negative charge altogether. In the same manner now, this oxygen is not probably completely removing hydrogen from here, but it is close to this hydrogen to show that okay, this electron belongs more to the oxygen than it is to the hydrogen altogether. But now there are mechanisms that can change the entire mechanism of the reaction, because formation of bond is involved altogether. So all of these things that we are having here in a way to balance the charge in transition states, they are also transient bondings altogether. But there are some mechanisms, there are some catalytic mechanisms that involve formation of bonding that will eventually change the mechanism of the whole reaction itself. And such one of them is the nucleophilic catalysis altogether. Is the nucleophilic catalysis. And let's look at an example of that.
So in this case, can we say we are forming like something like a very stable?
Yes, in a way, we are going to have a much stable intermediate in between the let me say reactant now and the product. Do you get that? That's what we're trying to say here. Because nucleophilic catalysis usually involve bond formation along the way, which eventually change the direction of the reaction. Sorry, change the reaction pathway. So now, and like I said, example of nucleophilic catalysis is seen in A-side transfer, in H-side transfer, and hydrolytic reactions. So let's look at this now. Example of that is hydrolysis of acetic anhydride. Acetic anhydride is CH3, C double bond O, we have O, C double bond O, and we have CH3. This is acetic anhydride. The point there is that on the norm, we could have probably do what we did the other time. That's half water here. And just say you have O, H1, H, and you have H, and then you have this. Is that correct? And then by the time you have this now, protons, this one becomes partially positive, this one becomes partially negative, and then the whole process of hydrolysis will occur altogether. But in the case of this now, we are using a nucleophile. So instead of using water, in this case, we're using a nucleophile. So, and the nitrogen here is carrying a 2 dot. That's what makes it a nucleophile. So it is having electrons that can attack the positively charged system. But now what I'm trying to say here is that what we are going to have here, by the time this one attacks this, we are not going to have a transient bonding. Bonds will be formed altogether. So, and that's what makes the difference between your electrostatic interaction and nucleophilic interaction. So in this case now, what will happen is that these two will react. So this will bind to this. This one can relate electrons to this, and immediately that happens, this will do, or this will come to this. Do you see what I just do? So I said the lone pair of nitrogen will attack this partially positive carbon that we have here. And immediately that happens, this one will go as a group. And that becomes what? So this becomes so that means the product now will go to be CH3, we have C double bond O, and then we are going to have A, we have N, and then we are going to have this. So this will be this, and this. And this nitrogen here carries a what? Carries a plus, because it's having 4 body now. Now, but what happens to this now? This one becomes that be C double bond O, and we have what? We have, so we are going to have O, C, we have O minus, and we have what? CH plus C. So this one will come out as acetate ion, this one will be like our intermediate. So this one here will be an intermediate, not a what? As it were a what? A transition state. Because bond is what? Is typically formed. So after this one is now formed, we can now have what? We can now have an hydrolysis. So when water is added there, what happens? Then this one now becomes what? This now one now go back. So you still have the what? You have your pyrimidine back together with your what? With your second what? Second acetate ion. Do we get the point now? So, but the point there is that in this case, what we have there is a what? Is a nucleophilic what? Catalysis. Because a nucleophile is involved, at the same time, a covalent bond is what is formed. And that is why we can say that nucleophilic catalysis is an example of covalent catalysis. Nucleophilic catalysis is an example of covalent catalysis.
So we said that whatever that is called, I think acetic anhydride, it breaks it down into water or what?
Now, no, I said normally, if you have an acetic anhydride, when you hydrolyze it, it's going to form two acetate ion. Because you are going to break this bond, this one will become, so this one will be an acetate ion, this side will also form a what? An acetate ion. So you are going to have two altogether. But we're trying to say there that, what we're trying to say there is that one thing that an enzyme will do to make the reaction more faster, or let me say to bring down the activation energy, is what? Is to form a what? A stable intermediate. Do you get that? So, but the same product will still be what? Will still be formed, which is what? Which is two acetate ion. So, like now, if this one is hydrolyzed now, together with, let's say, with it, so what happens is that this one becomes, we give one, that will give us CH3, C double bond O, and we have what? We have O minus. And this will come out as what? It still come back as our what? As our pyrimidine.
So that means that for this one is not acetic anhydride. What's the name of the compound?
Is it this intermediate that is formed? Is it the intermediate that?
The substrate, the very first compound.
No, this is still acetic anhydride. So, but you are saying that the reaction, or let me say the catalytic activity of the enzyme that works on this involves the use of what? Of pyridine rather. So this molecule is pyridine, sorry. And this intermediate is called.
It's like benzene. Is there nitrogen there?
Yes, it is like your benzene, but it has nitrogen within the what? Within the six membered ring. It is like your.
I can't see nitrogen.
There is nitrogen here. There is nitrogen here. There is no nitrogen here. There is no nitrogen here. So there is nitrogen in the compound. That's cool. The name of this intermediate is called acetyl pyridinium. Acetyl pyridinium. That's the name of the intermediate that is formed. pyridinium. We also have electrophilic catalysis that involve formation of covalent bond. And some of the reactions, some of these covalent catalysis, so covalent catalysis can be nucleophilic, or that's what we're trying to say. It can be what? It can be electrophilic. As much as probably bond is what? A rebond is what? Is being formed. And some of those reactions also include, some of these covalent catalysis reactions involve pyridoxal phosphates, Schiff base formation. Some of them involve Schiff base formation. SCHIFF, Schiff base formation. And thiamine pyrophosphate. And let's talk about intramolecular catalysis. Intramolecular catalysis. Yes.
You said there is electrophilic catalysis.
Yes.
That is the one that involves covalent. How do you differentiate?
Between the two. It's much better to say that we can have electrostatic so we can have electrostatic catalysis that is either nucleophilic or what's it called electrophilic. Let me probably put it that in code. At the same time, I can have a covalent catalysis too that is involving a what? A nucleophile or a what? An
Electrify.
But I only brought that because you are trying to say that all the difference between the former one we talked about and the one, but the major difference between them also is in terms of the bond formation. In one of them, there will not be bond formation, so the mechanism of the whole reaction will not really change. I'll get that. But in the second one, there will be bond formation. That's the major difference I can probably mention. We also have intramolecular catalysis. Okay, let's just write that. Intramolecular catalysis, of course, when the catalytic group is within the molecule itself. And that was probably going back to what I was trying to talk about the other time. So let's look at an example. An example of this is seen in what? An example of that is seen in what is it called now? In aspirin. In hydrolysis of aspirin. In aspirin we have something like this. COOH. And we have O. We have C double bond O. And we have C2. This is aspirin. So this is an ester. I'll get that. At the same time, what? A carboxyl group. So in a way, going back to what we are trying to say, we are trying to ask about the other time. So instead of if you are going to analyze this ester point now, so that this one forms alcohol and this one forms what? Acetic acid. You can easily use water. Okay. As I can also use another acid to stabilize the intermediate we form. But what I'm trying to say there is that instead of using one from the outside, the molecule itself is carrying an acidic group. Okay, that can donate a proton in order to stabilize what we have. In order to stabilize the intermediate, and it makes the process intramolecular. Do you get? Or I say that this now. Let me just try this thing that this will be double bond O and you have what? O minus. So by the time water binds to this, from what we did the other time, what happens? So you are going to have O, you are going to have H, and you are going to have what? H. So what I want to say is that I know by what we did the other time too, this one becomes of partially negative, this one becomes of partially positive, and you have a transient bond between them. That's the intermediate. So we're not going to say that if this positive charge will be balanced, how would that happen? This acetate ion can abstract the proton from what? From this water, from this HO now, and the thing becomes what? The intermediate becomes balanced. Altogether. And that's an intramolecular catalysis. Now, and one thing that intramolecular catalysis does is to increase the effective concentration. Is to write there that intermolecular catalysis increases the concentration, it increases the effective concentration of the catalytic group of the enzyme. So one thing we can probably say there is that if you are not going to have this here and you are going to use your normal base or your normal base from the outside, you are going to need what? 13 molar. But having this group here having this group within the molecule itself has already provided this 13 molar, and that's how the reaction rate increases altogether. So that's even the principle by which some of the protein they use. That it's not about they're going to bring in a molecule from the outside. So using their own molecule, their own chemical group within themselves also increases the rate of reaction of catalysis. Do we get that now? So when the catalytic group is within the molecule itself, then you have a what? An intramolecular catalysis. And I said one thing that it does what is to increase the what? The effective concentration of the what? Of that catalytic group. And another thing also that I probably want to bring out there is that let's say that the effect of this intramolecular of this group being part of the molecule now. Let me say that what is the basis for this particular effect that we are seeing in intramolecular catalysis. Now the basis for this is entropy. The basis for intramolecular catalysis and the increase in effective concentration is entropy. Is entropy increase? Let's put that with as there is a loss in the translational and rotational entropy of the two molecules involved, there will also be an increase in the internal entropy of the molecule when they are together. So in a way, there is a kind of how do I put it now? There is a kind of increase in entropy when these two things are together compared to when they are separate. I don't know if you get what I'm trying to say. So the basis for what happens in intramolecular catalysis, at the same time the increase in effective concentration is due to what? Is due to increase in the internal rotation entropy of the molecule involved. I don't know if you are getting what I'm trying to say. Another that also brings about this is what we call it that is about orientation too. Because if you are having substrates and enzyme together, but if they are not also put together in correct orientation, the rate of reaction will not still be fast. So two things must happen is that the substrate and the enzyme must first of all be together, and they must also be together in the right orientation. So those two factors are what helps the intramolecular catalysis than you having it to be intermolecular. Okay, let me probably talk about metal-ion catalysis, but we talked about that too when we're talking about electrostatic catalysis. We talked about that. When we talked about the fact that we talked about covalent catalysis altogether, and we said it can be nucleophilic and it can be It can be electrophilic. And when I was talking about the nucleophilic, so we looked at an example of nucleophilic whereby we have pyridine trying to being involved in hydrolysis of an ester bond. Okay. Now, but we now want to look at electrophilic catalysis under covalent catalysis. That means that formation of covalent bond is involved altogether. So that's what we want to look at now. So what is it? The first thing to ask is what's a Schiff base? When we talk about a base, I said that means you can accept a proton to form an acid. So now, but the Schiff base, and now what I want to talk about is that the Schiff base formation is under electrophilic catalysis. It's under electrophilic catalysis. The formation of the Schiff base itself is like it involves a nucleophilic reaction. But now let's listen to what I said. Look, I said the electrophilic catalysis itself involves a Schiff base. Okay, but the formation of that Schiff base involves a nucleophilic reaction between a carbonyl compound and an amine. So you always have a reaction between a carbonyl and amine. So this can this is a nucleophile. This nucleophile can attack this carbon plus, and then we are going to have that will be C double bond NR, and then we have R and we have R, and this is still carrying a dot. So the point there now is that this can accept this. So this is the Schiff base. So it can accept a what? A proton and become your C, and we have what? We have N, R, and we have what? We have H, and we have R, and we have R. That's what we have. So we can have this. And this protonated Schiff base can act as an electron sink. What that is that can act as a dumping ground for electrons.
Last one.
Yes, this last one. So this N here should be what? Should be plus here. Start with plus. So we're now going to be looking at different enzymes that works with Schiff base. The first one is acetoacetate decarboxylase. Acetoacetate decarboxylase. That's one of the enzymes involved in metabolism of ketone bodies. Acetoacetate decarboxylase. So the enzyme decarboxylates acetoacetate to give acetone and carbon dioxide. So let's see how that works. Normally, without the Schiff base involved, we have CH3, C double bond O, we have CH2, we have C double bond O, and we have what? We have CH what? Sorry, we have what? We have O. So this is acetoacetate. Acetoacetate. That's what we call acetate. Now on the norm, if this is not, what happens is that there will be removal of CO2 in the sense that this will come here. Okay. Immediately this one comes here, the bond becomes 5. The bond around carbon becomes 5. And what happens? That's like one of the bond must go. So it's going now, this one comes here. Yep. And then this comes here. So the point there is that this thing now will form CH3, C single bond O minus, and we have that double bond CH2 together with what? Together with CO what? CH2. So this later comes to what? To acetone, and then you have what? Carbon. So that's what decarboxylase does. But we're not saying that the enzyme, that's the normal reaction that we have without the what? Without the enzyme. So, but what the enzyme does, in order to make this thing what? To make it this to probably to lower the active energies what? Is by forming a what? A Schiff base. How do that? So it's like we can say that probably the enzyme in the active site has an amino group. How do that? There is a chemical residue that carries that has an amino group that helps this thing information of a Schiff base. So and let's now see how that takes place. So let's know that this is the enzyme with the what? With the NH2 group at the active site of that enzyme. So plus the acetoacetate, which is, we have said the reaction is always between carbonides and what we call now. And we have COO minus. So when this carbonide and this NH2 react, what happens? They form, now we have the E and we have N, double bond what? Double bond C. And then we're going to have what? CH3, CH2, and we have what? COO minus. That's the first thing that happens. At the same time, if it is, let's say probably if this one comes together with protons, rather than this one comes out at what? As plus, and you have what? You have H. So and these are protonated Schiff base. So the point there is that if there is nothing like a positively charged system there, removing this one will be a bit difficult. Compared to when you have a positively charged system at this point. So in a way, because this bond is already charged, I can simply, the removal of this bond here will be much more easier than not having a what? An enzyme. So in this case now what happens? I can now remove this one. I can remove this one to this place. Altogether. This bond can be broken. And this, sorry, and you know it will go to this place, to this middle. And what happens? The bond between on carbon becomes what? Becomes 5. So, and that means that one of these things must what? Must go. So I can easily remove the electrons on at this point to nitrogen. I want to get, and what will that be my intermediate now? My intermediate now will be what? That will be E, and I have, that will be what? That will now be E, and I will have what? Dash N dot dot, and I will have C, I will have H, I will have what? CH2, and I will have what? I will have CH3, together with what? CO2. So the point there is that this intermediate now, okay, sorry. So the point there is that this intermediate now is a much stable intermediate than what would have gotten at this point. Do you get that? Because we have an electrons, like an electron collector that is stabilizing the system, compared to what you have in this particular case. So the process by which this one lowers the application energy is by what? By formation of the what? Of a Schiff base. That's acetoacetate decarboxylase. Now imagine what can happen in this place, because so that you know, so that you also see that the formation of Schiff base is not only helpful to this place. It's not only helpful in the sense that this one is having as an electron sink alone. It's also helpful in the sense that it will also help in the formation of the reproduct. In the sense that, now let's look at this now. If this one comes back safely, altogether. Now the point here is that this one can go and what? And remove and bring in a what? And you know, this is a pi electron, abi? So this one can go to bring in a what? A proton. And this becomes what? So in a way proton here. So this pi electron can capture this. Alright, this pi electron can capture. So immediately this one will come back to this. The pi electron here can what? Can bring in an hydrogen. And then it becomes what? It comes to your E. And we have N double bond what? NH double bond C. And we have what? CH3. And we have what? CH3. Plus what? So we still have our CO2 here. Do you get that? So, and with this now, you can now get your what? Your ketone that you need. So the only thing is just that you realize this and then you get your ketone. Do you get? So the formation of Schiff base is acting in two ways. It's acting as an electron sink, and saying that it's also helping in the formation of what? Of the product that's intended. And that's for carboxy. That's for acetoacetate decarboxylase. Another example of an enzyme that works based on this is aldolase. And you know, in glycolytic pathways now, you know what aldolase does? That's the enzyme that change your 6 carbon system to 3. That's the enzyme that so that reaction also is based on what? On formation of the what? Of the Schiff base. We have CH2, we have OP, we have C double bond O, and we have C, we have H, and we have OH. We have CO, we have H, and we have R. So that's what we have in that particular regard. So the point there is that, you know, normally the reaction in glycolysis itself is what? Is fructose 1,6 bisphosphate turning into what? To glycylhaldehyde and dihydroxyketone. Sorry, dihydroxyacetone. So now, but we're trying to say that the breaking of this bond to this involve the what? The aldolase, and it involves this one. So let's say this one also plus what? Plus H2N, and we have what? We have E. So the enzyme have and NH2, an amino group that can form a Schiff base. So the first thing that happens is that this also the same thing happens. That will together with the proton. So you form a what? You form a proton. That will be C double bond what? Double bond N, and we have what? We have P, and all we are going to have what? CH2 O what? O, and then we have phosphate group, and then we are going to have what? We are going to have this double bond. We have C, we have H, we have OH, we have COH, and we have H, and we have what? We have R. Now that's what we have there. So there will be, so there is NH here, and then we have what? We have plus. Please don't forget that it's a protonated Schiff base. Don't forget that. Now the point there is that now, you know, if I'm cleaning it, a part must go as an aldehyde. That's a glacial phosphate, and one part must go as a what? As a dihydroxy. So that means, in a way, I want to partly cleave this bond. So I want to cleave the bond, and the first thing I will have to do is one, the bond between this O and oxygen can come here. All together. The bond between this, you know, this OH. This one can go away as a proton, and then the bond there will come what? This bond there will become what? A double bond. But now, later I move this bond to this place now, what happens? This bond here becomes what? 5. So I have to what? I have to remove this. So one of them, so in a way, this one will now come to this one, to come to this place. How to get out? But because there is already an electron sink here, what happens? This one can easily what? Can come here, and the thing becomes a what? A stable entity. You know, if I move this bond here to this middle, how to get out? What I have here allows me to do that, because this one can take in the electrons. And that's what we have been saying about the Schiff, that is a what? It usually serves as an electron sink. And in that way, it makes the reaction it makes the intermediate a bit more stable. This place now, immediately we have that, this one that we have here now, we break into two products. So this below part, from this part downward, what would be the product? That would be C double bond O, we have H, and we have what? R, which is the part that forms the aldehyde. All together. So, but the upper part that we have here now, what are we going to have here? What are we going to have here? That would be C, we have H, we have what? OH, and this place called double bond C. You know, this one moves to this place. The one that moves to, and then we are going to have what? We are going to have single bond double bonds, and then we are going to have single bond N, and we have what? We have the enzyme, we have H, and we have dot. And on top we are going to have what? CH2, we have what? O, and we have what? P. So you can see that because of so the reason why this electron can be what? Can be here, and the intermediate will not be disturbed, is because we already have what? The positively charged N plus A. Do we get that? And N can carry what? The positive, can also carry what? Lone pair of electrons. And that's how we are. So what now happens at this point from what we did the other time? So how do you break this now from what we did the last time? So in the same manner, this can come back, and this one we have shot in what? An hydrogen. And then the product now, this one changes to what? That becomes C double bond N, and we have what? We have C. We have CH2, we have what? OP, and then we are going to have what? That will be CH2. So we are going to have H, and we have what? OH. And this will become what? It will become what? Plus. Don't forget an NH. So what we have the last thing to do? We do what? We aldolase. And then this one becomes the ketone back. And then you still have a what here inside that. The aldolase can work from this side to the back. It can also work from the back. You know, it can work, the reaction is reversible. So your aldolase can change DHAP and glacial phosphate to fructose 1,6 bisphosphate. And you can also break it down towards that. So we looked at two enzymes now. Yes. Acetoacetate, decarboxylase, and then aldolase in terms of Schiff base formation. Now that one I want to talk about is Now, and that's in terms of what of chemistry. Another one I want to talk about is the pyridoxal phosphates. The ones involved endophilic catalysis now under covalent catalysis involving pyridoxal phosphates.
Pyridoxal.
Phosphates. Now the major difference between the first one that we looked at now, the two of them is involving what's called Schiff-based formation. Let me put that. The two of them is involving Schiff-based formation, but the difference between the two is the point that in the first one, the amino group is part of the enzyme. How to do that?
Okay.
It's like the amino group that is used for the Schiff formation is what is within the enzyme itself. It's an amino acid that carries that amino group. But in the case of this one, the enzyme is nearly a coenzyme, and that coenzyme is the pyridoxal phosphate. So the enzyme in this case now, in terms of that, the enzymes that are probably involved in what's going, they're actually involved in reaction in metabolism of amino acids. So what the group that that pyridoxal phosphate carries is the carbonyl group altogether. But it is the amino acid that will give the amino group. I don't know if I'm making sense. So most times the enzymes involved here are enzymes that are involved in amino acid metabolism. Sometimes you can probably remove amino group from amino acid, and then you have a keto acid. You can sometimes remove carboxylic acid, and then you get amine. So all of those reactions now, they are reactions involving this coenzyme. So most of those enzymes involved in those reactions needed pyridoxal phosphate as their coenzymes. But the activity of this pyridoxal phosphate is also in terms of forming a Schiff base. Do we get the point now? So let's just do some reactions, and then we can probably now see how it goes down. But I think you understand this pattern. Let us start by drawing the structure of pyridoxal phosphate. We have
I want to do my slide.
No, sorry.
We have H plus. So this is also this, and then we have here we have OH. Here we have CH3, and here we have CH2,
What's this?
and we have phosphate. That's this pyridoxal phosphate. The enzyme that carries this thing, like I said, they are always involved in amino acid reactions or metabolism. So they can all tell out the pyridoxal phosphate can always combine with any amino acid. So let's give an example of an amino acid is probably we have C, we have NH2 and then we have R, we have what else? We have COO, let's say minus, yes, and we have we have H.
So it's still like that Schiff base.
Yes, yeah, it's still like this. So the same thing, but the only thing is that the amino group is not in the enzyme, it is from an amino acid. I'll get that. So it's not about in this case now, the enzyme is having a pyridoxal phosphate that is having a carbonyl. How to get that? The enzyme is having, in the other one, the enzyme is having an amino that is combining with carbonyl compounds. Do we get that? But in this case now, the enzyme is having a pyridoxal phosphate that is having a carbonyl that is now combining with an amine. Do we get the difference between the two now? So in a way, when this and this combine, what happens to them? They form a what? They also form like a Schiff base. Let me just draw the product now. If these two combine, I'm going to draw the full structure again. I'm going to have CH, and that's the double bond N, and we have COO minus, we have R, we have H.
Eh?
And then this one, you only use the amino acid. The NH2 of this has combined with this carbonyl.
Okay.
And then we now have C double bond N with the remaining part of the amino. But now this one will now go up. Now build the ring system. I'm not going to draw the full structure again. I'm just going to draw the one. So here we have this. Here we are going to have a branching, and here we have a branching. And this N here carries the what? Carries the blood. Now, the issue with this reaction now is that this single thing that you have here, this single thing that you have here, can undergo several reactions depending on what you want to do. Now, in some cases, you can now, because the thing is, what you have here allows you to remove what, any of this group on the what, on the alpha carbon. Okay, you can remove the what, you can remove the what, you can remove this carboxyl group, you can remove the what, the R group, you can remove the what, the hydrogen, you can remove any of these things, any of the things, sorry, any of the group around the what, around this. And in some cases, you can also remove the what, the amino itself. Do you get that? So removal of all of this group around the alpha carbon is what is possible after the formation of this what, of this Mr. Man.
No.
So now the first one, let's write removal of alpha. So I've said with this particular thing being formed, you can remove any of the four groups around the what, around the alpha carbon. So let's write the first one, removal of what, of alpha hydrogen. Now, removal of alpha hydrogen can lead to removal of the alpha hydrogen. Removal of alpha hydrogen can lead to racemization. That is changing your D amino group to an held amino acid. You can use it to convert a D amino acid to an held amino. That's racemization. It can also lead to transamination, which leads to formation of pyridoxamine and alpha ketoacid. So that's under transamination. You know, the point there is that you can use the method to remove amino group from the amino acid. Like I said, if you remove amino group from the amino acid, you get your keto acid. At the same time, you can now add that amino group carried by so the amino group leaves the amino acid and go to pyridoxal. And that's why you have pyridoxamine. But now the pyridoxamine can now transfer that amino group to another keto acid. And that's where it comes as a word, as transamination. It can also work in terms of beta decarboxylation. So please note that it is not, you are not removing the word, the alpha. So the one they are talking about here is not about this alpha one. It's value when your R group has, when the R group contains what? Contains a carboxylic acid. Okay. You know, you can have, let's say, your R group here is what? Probably CH2. I have what? COO minus. So you can use it to remove what? To remove this part where you have aspartic, like you said. You can use it to remove that. So let's keep it as that. You can write it that this is similar to acetoacetate decarboxylase reaction. The next one is that removal of the alpha hydrogen too. Removal of all of these I'm mentioning, they are still under removal of the alpha hydrogen. That's why I said that single reaction can lead to several things. When you remove the alpha hydrogen alone, I think what happens? What we're trying to say there is that if I remove the alpha hydrogen here now, what does that imply? That means that this one comes here.
Yes.
How's it that? This one comes what? This one comes here. Let's go. The bond here comes to this middle. The bond here comes to this middle. Now what now happens to the ring 2? The ring here comes here, and this Mr. 1 comes to what? Comes to nitrogen. Do we get that? So it is this N, you know it's N plus. So this one will serve as the what? As the electron sink.
Okay.
So that means that the product that will now be what? Now be C single bond N. Abi, that what? Double bond what? Double bond C, and we have what? R, and we have what? COO minus. And we still have what? H here. And this one will now be what? Double bond. And then we have our ring structure.
How is it not for this?
So this one will now carry what?
Carry that in as this key.
Okay, so you know here it was carrying a plus, but now it's carry what? A lone pair. And then we now have what? We have this, and we have what? We have this. And then we are going to have this, and this. Do we get that? So this one. So we're now saying that this one that we have here now can undergo several things. In the sense that you can now one of the things you can have that you can add hydrogen back. You can add hydrogen, that hydrogen again, and then you get what? That's when you have addition of what? Addition of hydrogen what? Hydrogen back. That will give us what? That will give us racemization. How do we get that? That's one. The next one I talked about after racemization is what? Transamination.
Okay.
So that one you forward, that you forward, removing the word, the amino group. You click this part. When you realize this part, so this part becomes for pyridoxamine, and then you have this one as what? As your keto acid. So this one is when you realize. So when you realize this bond here, this alpha double bond. So that becomes so that's what that's under transamination. Transamination. So that's the address of the word of the alpha double bond. This alpha, when you realize this one becomes the amino group goes to this, and that's pyridoxamine, and then one comes out as ketone acid. Do we get that now? Now that one that we have is that I'm talking about which one did I talk about now?
Beta
Decarboxylation. So that's probably if, like I said, if your have a CH2 and you have what? CO minus. So you can easily remove this carboxyl group altogether now, and then you still get what you get your product. So you can remove this one away, and that's when you have your beta decarboxylation. Now I said that, so it can also lead to intervention of side chain. Now you can also have the next that we have now is after the removal of alpha hydrogen. The next that we have is what? Is alpha discarbonation. You can we talk about alpha removal of alpha hydrogen, and we mentioned like 4 things under it. The first one is what? Is racemization, transamination,
beta
and then
decarboxylation,
decarboxylation
of side chain.
Okay. Now the next one that we now have after the removal of the alpha hydrogen is the alpha decarboxylation. We also have alpha. So in that case, that means we are going to remove the alpha COO. That's what that implies. Now you can just add in that decarboxylation, the alpha decarboxylation can lead to formation of amine and pyridoxal. Let me start from what we can familiar with. The first one is that I remove this one. The amino acid can come out as what? As amine, and this one will come out as what? As the normal pyridoxal phosphate. Is that correct? Now, but the point here is that this amino acid can also come out as what? As the aldehyde. It can come out, the point there is that means that you are hydrolyzing this bond between this N and this C. So the idea that I can hydrolyze the bond between this N and C, and I'll get what? I'll get pyridoxal and amine of that amino acid. In a way, I can also hydrolyze the bond between this N and this C. In that case now, I'll get the what? This one will come out as an aldehyde, while this one will come out as what? As pyridoxamine. So you can either get amine with pyridoxal, or you can get aldehyde with pyridoxal group, depending on which of the bond you are playing. So the removal of the alpha carboxyl group, or let's say alpha decarboxylation, can either lead to formation of pyridoxamine with aldehyde, or amine with pyridoxal phosphate. But the idea, like I said, is that you can clip the bond between this N and C. You can clip the bond between this N and C. And that's what we're talking about the two different products. Last one that we have here is thiamine pyrophosphate. Thiamine pyrophosphate. Thiamine pyrophosphate is another coenzyme like pyridoxal phosphate. Thiamine, and it's also under electrophilic catalysis.
Is it
Thiamine pyrophosphate. You know what pyrophosphate is now? Pyrophosphate is two phosphates. So when you have two phosphate group attached to thiamine, then you have a thiamine pyrophosphate. So and there's another coenzymes too. This is using elongating carbon chain. That is formation of carbon to carbon bonds. It can also be involved in breaking of carbon to carbon bond. So it can be to elongate. It can also be to cleave. So example of enzyme that works in that. Example of enzyme that where you have thiamine pyrophosphate is transketolase.
I feel like giving you a hug right now.
But what is this?
Alan Freight.